The cross product can be mystifying. Its definition is strange, sometimes hard to remember. It's much more complex than the definition like the dot product, where we have simply that A dotted with B is, and you got two ways to write it. You got magnitude of A times magnitude of B times the cosine of the angle between them. You've got the sum of the product of their components. This is not at all as simple as the definition of the cross product. Now we do have a vague geometric intuition that you have two vectors, A and B, and their cross, so this is A, this is B. If you take the cross product of A and B, we have this intuition that that cross product will be a vector C that is perpendicular to both A and B. And this is good, but it's not so formal. So what I want to do in this video is take this geometric intuition and make it concrete. We're going to constrain what the dot product is by forcing it to be perpendicular to both of its input vectors. And by doing that, we are going to come up with ourselves. We're not going to rely on a convoluted definition outright. We're going to come up with ourselves what a reasonable way to define the cross product is, so that it follows this nice property that we want out of it. So let's think about how we can do that. Well, the first thing we want to do is to formalize how we're talking about perpendicularity. And specifically because I want a more general word for perpendicularity, I'm going to use the word orthogonal. So orthogonal. And orthogonal really just means that if you have two vectors A and B, that when you dot them together, they equal 0. And it is very similar to perpendicularity, with the exception that A and B, if they're orthogonal, they can be 0 vectors, whereas if they're perpendicular, they can't be 0 vectors. They must be non-zero. Anyway, with that tangent aside, we know that to be orthogonal, you need A dotted with B to equal 0. Well, in this diagram, we have three vectors, A, B, and C, and we want A and C to be orthogonal, and we want B and C to be orthogonal. So, if we're going to write this down, this should almost be our constraints for the cross product. So, constraints for cross product. We can write these down that our output C, which is A cross B, we know that we want two things to be true. If we were to dot A with A crossed with B, this should get us 0. And similarly, if we were going to dot B with A crossed with B, this should get us 0. Well, now that we have constraints for what a cross product might look like, let's think about how we could use these to define the cross product. And to do that, I want to take a little foray into a bit of an odd way to think about determinants and how that can be useful for thinking about what dotting might mean for that type of determinant, and then how we can extend that to making a cross product definition that'll satisfy that perpendicularity that we're going for. So let me introduce a type of determinant, and we're all familiar with the basic determinant. If you have some variables here, A, B, C, and D, here you're going to take A times C. You're going to have, that's D, not C. So A times D, and then you're going to subtract B times C. That is the base determinant that we're familiar with. What if I replaced A and D instead with basis vectors? This does sound quite strange indeed, but roll with me. This will start to make sense soon. So we replace A with I hat and B with J hat, and we keep C and D the same, although I'm going to write them as two components of a vector, so as A's x component and as A's y component. Well, if we just go forth and go and compute this determinant, what we're going to end up with is the vector AY times I hat minus AX times J hat. Now that's pretty interesting, but what gets really interesting is when we take this determinant and we dot it with another vector. So let's say I wanted to take this determinant, so the determinant of I hat, j hat, a is x, and a is y, and I wanted to take the dot product of this with another vector, b, and we could also write b as b's x times I hat plus b's y times j hat. Now that we have this, we can remember this determinant here equals this expanded quantity here. So if we're going to take the dot product, we have to match up the I coefficients, the I hat coefficients, with the j hat coefficients. I should really be including this minus sign there. It is part of this ax. And if we evaluate this out, if we think about this dot product now, we're going to have b's x component here times a's y component. You'll see why I'm writing it like I am in a minute. And then we're going to have minus b's y component times a's x component. So this is fine. Why did I write it with the parentheses? Well, another way of thinking about this is as another determinant. So how could we write this? We could write this as the determinant of, well, we have this multiplication and then this negative multiplication. So maybe this bx and by, maybe this is the top row. So we have bx and by, and then ay and ax. We keep these here. The ay is going to go on the right, so that it's multiplied by the bx, and the ax is going to go on the left, so it's multiplied by by. And we have this determinant. And what is interesting about this determinant is that the ax is in the same place. The ax and the ay, that vector is the same as this original vector before we dotted it. The only thing that's different actually between this determinant over here and this determinant we started with is that the basis vectors are now gone. We have replaced the i's and j's with the vector b. And if we think about it, it makes a lot of sense that that would happen, because each component of the vector that we were dotting with, like the bx, became multiplied with the I, so the bx took the i's place, and the by is with the j, got multiplied with the j, so the by took the j's place. And this also works in 3 dimensions. So in 2 dimensions, we've seen that dotting a vector with this odd way to talk about a determinant almost makes that vector usurp the basis vector's positions. Well, if we do this in 3 dimensions, we could consider that we have the basis vectors I hat, j hat, and k hat. And I'm just going to write my vectors. I won't write out all their components. I'll just write a and b. So you can imagine that they have their x and y components on either side. This, if we were to dot this with a third vector, c, just using our intuition and what we learned from the 2-dimensional case, and you can prove this on your own if you feel especially into algebra today, you can see that this c here is going to take the place of I, j, and k. So this c will take the top row, and then this a and the b will stay where they are. So this in of itself is quite an interesting observation about how determinants function when we have a row as basis vectors. Now I want to make one more observation before we talk about how we can use this construct to define a reasonable definition of the cross product. So my question for us now is, when does a determinant, so when does a determinant equal 0? When does that happen? Well, there are many ways we could go about thinking about this problem, and one of them is with the geometric intuition behind a determinant, which is inherently about area. So if we think about the determinant of a vector a and a vector b, and again I'm writing them in this way, you can imagine that there's the x's, the y's. If we think about this determinant, this is saying, okay, if we have, so we have our I, sorry, not I, so used to thinking about basis vectors. This is our y and our x-axis, and we have our vectors displayed on here. So this is our vector a, and this is our vector b. This determinant represents the area of the parallelogram described by extending these vectors on themselves. The area of this parallelogram is this determinant. You can go ahead and prove it if you feel like it, but this is the geometric understanding of the determinant. And in 3 dimensions, if I were to add, say, a third vector here, so c into our determinant, and we can draw c out and be like this. If we were to draw c out, now our determinant represents the volume of this shape here, which is called a parallelepiped. It's a pretty fun name to say, especially 5 times fast parallelepiped. And this area of the parallelepiped is the determinant. So now if we think, what would happen if 2 of these vectors were equal? So what we're trying to figure out now is what would happen if we had the vector a, the determinant of a, b, and maybe a again. So we have this determinant of a, b, and a. Well, this, as we saw before, this would translate to, so we have kind of now our x, y, and z axes. So x, y, z, although the labeling doesn't matter too much. We have our a vector be going out something like this, our b vector going out something like this, and then we don't have a different third vector. The third vector is a again. So now we have 2 a's. Well, what is this determinant? Now we might think that it's going to be just the same as we were doing before, the area of the parallelogram. But when we're talking about determinants in 3 dimensions, we're fundamentally thinking about volume. And the volume of this parallelepiped, if you think about it that way, that a parallelogram is a parallelepiped with 0 height. And whenever we have 0 height, we're going to have no volume. So we can think about this as having 0 volume. And if the volume is a measure for what the determinant is, 0 volume would tell us that the determinant equals 0. So this is really interesting. Whenever we have 2 vectors, so 2 vectors in a determinant that are equal, the determinant equals 0. Well, based on this observation, and the observation that we can implant a vector into a determinant with basis vectors, I think we are finally ready to come up with a good definition for what the cross product of 2 vectors could be. So let's say we've got a vector a, and we've got a vector b, and we want to cross them together. One way that we could define this operation would be as the determinant of I hat, j hat, and k hat of the vectors a and b. And if we go with this definition for a little bit, let's see how it works into our constraints that we defined above, that the vector a, when we dot it with whatever we get out of our cross product a dot b, a cross b, this should equal 0, and also that b dotted with a cross b, that this should also equal 0. Well, if we remember from up here, when we have basis vectors in a row, dotting with another vector is like that vector taking over the position of the basis vectors. So let's consider a dotted with a cross b equals 0 first. What we get when we say a dotted with a cross b with this definition is the same thing as a dotted with this determinant here, the determinant of I hat, j hat, k hat of a and b. And if we think about this dot product as a taking over the row, so a takes over ijk, then this becomes the new determinant, the determinant of, and then a and b, a and b. And this determinant here, as we just saw, this is going to define a parallelepiped with 0 volume. This determinant will equal 0 because we have 2 equal vectors. And similarly, if we were to do this for b, we would be saying, and I'll just write this out in one color to keep it quick, b dotted with the determinant I, j, k, with the vector a and the vector b. This is going to be the same as b taking over this row, so b takes over ijk, and then you have a class with this b. You have 2 equal vectors in the determinant, so your determinant will equal 0. So I hope you see now that this way of talking about determinants, where we have the basis vectors in one of the rows, whenever we dot it with any of the vectors here, that is going to involve that vector usurping the position of the basis vectors, which will result in a determinant of two equal vectors, as we've seen here in the case for A and B. And whenever we have a determinant of two equal vectors, it is always going to describe a shape with zero volume. So the determinant will equal 0, so the dot products will equal 0, which will tell us that that fundamental geometric intuition that we started with, that A cross B should be orthogonal to A and B, that this is going to be true. So, hope this video vaguely made some sense to you and gives you a stronger sense for why the cross product is this definition here.